Imagine 50 million screaming chefs crammed into a single, massive commercial kitchen.
Oh man, that sounds like a total nightmare.
Right. Every single one of them is tasked with cooking a completely different five-course meal. And they all share the exact same stoves, the same pots, the same ingredients.
But I'm guessing they aren't communicating with each other?
Exactly. They aren't talking at all. They are just moving, grabbing, and chopping as fast as physically possible.
Which is just a recipe for catastrophic system-wide failure. I mean, you would have kitchen fires, ruined ingredients, and ultimate gridlock within seconds.
You would think so, yeah. But what if, instead of burning the kitchen to the ground, that sheer, overwhelming density of overlapping chefs actually forced a structural shift?
A structural shift.
Yeah, what if, simply because they are so densely packed together and moving so fast, they hit a threshold where they suddenly begin to anticipate each other's movements? They share ingredients flawlessly without speaking, and the kitchen snaps from pure entropic chaos into a highly ordered, fluid symphony.
It sounds like science fiction. But mathematically speaking, that is exactly what happens in highly dense, complex computational systems.
Welcome to today's deep dive. I'm your host and joined as always by our resident expert. For you listening, our mission today is to explore a staggering 120-page white paper titled Convergence Lattice.
It is quite the read, let me tell you.
It really is. We are going to decode how all of our fragmented digital systems like AI agents, edge computing hardware, programmable finance are all quietly merging into a single recursive substrate.
And more importantly, we are going to look at how hard mathematical limits will dictate our ability to coordinate these autonomous systems, both here on Earth and eventually off-planet.
Yes, and before we get into the heavy math, we have to talk about the author. Because what's genuinely fascinating about this paper is its origin.
Oh, absolutely.
The author, Martin B. Joseph, working out of the Stambic Accelerate office in Botswana, didn't start with a neat, traditional academic problem statement. He literally stitched together 4 different research notebooks spanning AI, hardware physics, economics, and topology.
Right. Disciplines that were each convinced the other 3 were speaking complete nonsense.
Exactly. He had to use what he calls 4-dimensional thinking to realize that this global structural evolution is already happening right under our noses. And the mind behind all this is a 20-year-old polymath working out of Botswana. I mean, come on.
20? Wait, what the hell were we doing at 20? I was probably failing my first-year exams and eating instant noodles.
Exactly. I was binge-watching shows and pretending I understood basic calculus. Meanwhile, this kid in Botswana is writing 120-page mathematical white papers.
And from Botswana, an African country where, if we heard right, he's faced a ton of rejections from the usual academic status quo. Africa is clearly producing its own prodigies, too, you know?
Oh, for sure.
Like little Abel in Ethiopia explaining multidimensional physics at 7, or Chidi in Nigeria, who built a whole offline AI coding platform in his early 20s.
It is so wholesome. In that rare interview, he actually said he believes in Musk's vision, and then he was joking around saying he only hopes Elon would take care of his health so he lives long enough because the 22nd century is going to need him.
Holy shit, that is wild. The kid's already thinking on a 22nd century timescale while the rest of us are just trying to make it to next week.
Right. It is so foresightful. It's almost funny. I'm calling it now. I wouldn't be surprised if in a few years, Martin builds the next multi-billion-dollar company, or gets noticed by the deep hardcore technologists like Elon Musk.
I would absolutely bet on that.
So getting into his handwritten derivations in the source material, they are incredible to look at. You can literally see him wrestling with these concepts on the page. We are going to translate those very dense mathematical proofs into a roadmap for you today.
And let's start by diagnosing the baseline. Where are we right now?
Right, because currently our technology feels incredibly dense, but it certainly doesn't feel like a flawless symphony.
Well, right now we are in the chaotic kitchen. We have edge compute nodes, autonomous AI agents, and financial algorithms, all sharing the exact same physical and digital space.
But they lack a unified coordination layer, don't they?
Exactly. They overlap, but they don't align. Which brings us to the first massive concept in the paper. We need to break down the ERM.
The entropy rate margin. Let's take this slow. Beat 1, we name it simply the ERM. Martin uses this to measure the exact friction of that overlapping chaos.
Right, and for beat 2, The everyday analogy. Think of it like a city where everyone has a car, but there are no traffic lights or lanes. Everyone is moving, but no one is getting anywhere efficiently. It's the wiggle room a complex system has before internal friction turns into pure noise.
That makes sense. So what is the actual equation for beat 3?
The equation calculates the gap between the total available interaction space, meaning everything the system could potentially do, and the effectively coordinated space, which is what the system is actually doing efficiently.
Okay, let me unpack this. Let's look at high-frequency trading algorithms, or AI agents, trying to secure cloud compute. They're all operating in the same environment, so the interaction space is huge.
Huge. Millions of operations a second.
But if they're constantly stepping on each other's toes, the ERM measures that exact drag on the system's efficiency.
Precisely. It measures the delta between motion and progress.
So here is my question. The instinct of the entire tech industry for the last 3 decades has been to just build faster infrastructure, broader bandwidth, zero latency fiber optics.
Right, the usual solution.
Yeah, if we just build faster networks, doesn't the ERM naturally go down? Don't we just solve the congestion by building a faster highway?
What's fascinating here is that the math proves the exact opposite. Faster networks actually make the ERM exponentially worse.
Wait, really? How does speeding up communication destroy efficiency?
Because as the density of these autonomous agents increases, implicit coordination breaks down entirely. When network latency drops to near zero, these agents don't have those microseconds of delay to observe what the rest of the system is doing.
Oh, I see. So imagine 2 highly autonomous AI agents spotting the exact same arbitrage opportunity at the exact same millisecond.
They both lunge for it simultaneously, they execute at the same time, they collide, they create overlapping redundant work, and they lock up the shared resources.
Wow, so it's not that they fail to interact, it's that they interact too much too fast.
Exactly. They are locally optimizing for their own tasks, but in doing so, they completely destroy the global efficiency of the network. Faster networks just mean they collide harder and faster.
Okay, so if we can't build our way out of this with faster cables, what actually happens when we keep cramming millions of new autonomous agents into this substrate? Does the whole thing just crash?
Not necessarily. This is where we hit phase transitions. If you keep increasing the density of agents in a confined interaction space, the system eventually hits a critical threshold where it snaps from totally disordered to highly ordered.
Holy shit, that phase transition is brilliant.
Yeah.
It's like liquid water reaching a specific temperature and suddenly crystallizing into solid ice.
Yes. The structure of the environment itself forces a recursive order upon the agents.
So the screaming chefs suddenly become telepathic. The density itself becomes the coordinating mechanism.
Yes. And this is but that phase transition is incredibly dangerous because right at the edge of that crystallization is something Martin calls the Coordination Inversion Threshold.
The CIT. I saw his notes on this. He spent weeks stuck on this specific derivation. How does he mathematically define that tipping point?
Let's break this into 3 beats again. Beat 1, the name, the Coordination Inversion Threshold. Beat 2, the analogy. Imagine a delicate house of cards where adding just one more card doesn't just fail to build it higher, it brings the whole thing down.
The mathematical peak where adding one more agent makes the whole system less efficient.
Exactly. Up to that point, adding agents might increase overall utility, but cross the CIT, and that single additional node causes the underlying lattice to fracture into competing parasitic microeconomies.
And for beat 3, the actual equation. You read the handwritten derivations. How insane is that non-commutative part?
It is wild. You can literally feel how hard Martin was wrestling with this derivation. He crossed out 3 versions in the margins before landing on this.
Because he initially tried to map this using standard deterministic equations, right? Clean, predictable models.
Right, but deterministic math completely failed to predict the CIT. He had to build the model using stochastic random noise because in a dense recursive system, averages are liars.
I love that line from his notes. Averages are liars. But what does that mean in practice for these AI agents?
It echoes what John von Neumann warned us about decades ago. You might calculate that, on average, 1 million AI agents are operating at 95% efficiency. But in a recursive lattice, variance is everything.
So a tiny fluctuation, say, one agent making a weird local decision, doesn't just isolate itself, it propagates.
Exactly, because their outputs are the inputs for the next layer of agents. To capture this, Martin had to use non-commutative operators in his math.
And for you listening, non-commutative simply means the order of operations permanently alters the state. If Agent A copies a database and Agent B deletes the original, the order of those actions changes physical reality.
Right, it's like deleting a file before you've copied it versus copying it before you delete it.
So when millions of these non-commutative transactions are happening concurrently, a single variance at the CIT threshold cascades into a structural collapse. The entire system tears itself apart.
Which is terrifying. The system doesn't just slow down, it actively destroys its own utility.
So if adding one more agent crashes the system, how do we survive the CIT trap? We obviously aren't going to stop deploying new AI agents.
We can't. The only way out is to fundamentally change the nature of the interaction itself. The agents can't just communicate data, they have to transact trust natively.
Which brings us to programmable value. This is the mechanism that prevents the lattice from shattering. Explain how this works, because it goes way beyond traditional smart contracts.
It really does. Martin brilliantly synthesizes two mid-century scientific giants here. Claude Shannon, who gave us information theory by reducing complex networks to Boolean logic, and Norbert Wiener, who gave us cybernetics, the study of dynamic feedback loops.
So Martin is taking Shannon's logical primitives and wiring them directly into Wiener's cybernetic feedback loops.
Precisely. In the convergence lattice, the value transfer is the feedback loop. Agents become active economic participants, initiating what he calls atomic value flows.
So the token isn't just a static ledger entry, it's executable logic.
Exactly. An agent sends a contract that essentially says, I will route this micropayment of value only if this specific compute task is verified by the local environment, and the moment it is verified, it automatically triggers this secondary supply chain.
But I have to push back here. If every single autonomous agent in this global lattice is acting as its own mini-bank, executing complex conditional logic for every single microtransaction, aren't we just building a vastly heavier, more bloated system?
That is the genius of what Martin terms coordination compression. It seems counterintuitive. You would think adding complex logic to the money makes the system heavier.
Yeah, doesn't it explode the computational overhead?
No, because by encoding the rules directly into the primitives, into the value itself, the system actually prunes away massive layers of unnecessary coordination.
Walk me through that contrast. How does this actually prune the coordination?
Look at a traditional system. Agent A wants to utilize a sensor. It has to ping a central server, wait for authorization, lock the database, confirm the data, and then trigger a separate payment gateway.
Which requires external trust, latency, and constant state checking.
Right. Now, look at the convergence lattice using programmable value. The smart contract itself holds the state and the authorization. There is no central server to ping. There is no background check. The trust is structurally embedded in the interaction.
Oh, wow. So the structure itself absorbs the trust overhead.
Exactly. It effectively shrinks the ERM. The lattice scales not by adding more management layers or faster cables, but by making the interactions themselves entirely self-regulating.
Okay, the system doesn't crash. It becomes telepathic.
Wow.
That is a profound paradigm shift. We survive the CIT by managing trust through programmable value.
And it works beautifully here on Earth, where our data centers are connected by fiber.
But the paper doesn't stop at the edge of the atmosphere. Martin pushes this mathematical framework to the absolute physical limits. What happens when this substrate expands to orbital satellite clusters or rovers on Mars?
This is the ultimate stress test, semi-multiplanetary coordination, and the first, most brutal physical constraint the lattice hits is latency.
Because no matter how elegant your programmable value is, you cannot code away the physical speed of light.
You cannot. Latency strictly enforces interaction tiers. You can have incredibly low latency clusters here on Earth, but the moment an Earthbound agent tries to coordinate an atomic value flow with a node on Mars, you hit a hard physics limit.
Right, you can't close a feedback loop efficiently when the signal takes 20 minutes to travel.
Exactly. So when we move off-world, extreme autonomy isn't just a nice feature to save bandwidth, it is mandatory for the lattice to survive.
Let's break down his off-world equations, because reading the raw variables is a bit daunting. Let's do the 3 beats. First, the names. The autonomy threshold and environmental chaos.
Right. For the analogy, think of a remote worker in a war zone. If they have to call headquarters for permission every time a bomb goes off, they won't survive. They need the autonomy to react instantly to the chaos.
And for the actual math beat, he balances 2 massive forces against each other. On one side, the proportion of decisions the remote system is allowed to make independently.
And on the other side, the environmental heterogeneity. Basically, how chaotic and unpredictable the remote environment is, sudden thermal drops, solar radiation spikes, things like that.
So if the environment is highly chaotic, but the remote node's independent decision-making allowance is too low, it has to wait for Earth's permission to react.
And during that latency window, the environment destroys the node. The latency bottlenecks the planetary system, the flows fail, and the lattice shatters.
But there is a second variable in his multiplanetary math that is even more critical: energy reuse.
Yes, that concept is absolutely critical. In these off-world equations, systems don't just burn energy, they leak it through time.
Right, because when a Mars rover is waiting for a delayed signal from Earth, it is sitting idle.
And those idle cycles are leaked energy. If the energy reuse efficiency of that local node is low, the off-world lattice literally starves to death waiting for instructions. It runs out of power before the feedback loop can close.
What makes this entire deep dive so compelling is that this isn't just theoretical notebook math. The sources we're looking at include real-world validation happening right now.
Oh, absolutely. Look at Andrei Karpathy's recent work on distributed model convergence.
Right. He noted that AI systems with high internal energy recycling are showing vastly greater convergence across distributed nodes, which is a perfect real-world manifestation of Martin's predictions.
And then there is Pranav Mayana, who recently built a first principles physics simulation for orbital compute clusters.
Yeah, he looked at the hardcore engineering constraints, thermal limits, radiator mass, latency, and his conclusion was that autonomous self-directed maintenance is the single hardest constraint for computing in space.
His findings map almost flawlessly onto Martin's mathematical levers for environmental chaos. Martin's theoretical math is successfully predicting actual bleeding-edge engineering challenges.
Which perfectly sets up the final parting thought in Martin's white paper. He projects the ERM into the deep future, mathematically summing the layers of abstraction over time. But the multiplier he uses at the very end of this recursive equation is the golden ratio.
It is such a stunning realization.
He takes the mathematical signature of organic evolutionary growth, the same ratio that dictates how Nautilus shells spiral, and introduces it into a rigorous paper about digital infrastructure.
He is explicitly suggesting that as these autonomous systems scale to a planetary level, they stop acting like traditional machines. They grow organically. The structure carries its evolutionary history with it.
We aren't just designing a top-down network architecture anymore. We are seeding a digital lattice that will grow and crystallize organically, entirely dictated by the harsh constraints of physics.
And looking at the sheer scale of this autonomous evolution, it leaves us with a deeply provocative question. If this convergence lattice requires ever-increasing levels of embedded, independent autonomy just to survive the physical latency and energy constraints of deep space, at what point does human oversight become the primary bottleneck?
That is the ultimate question, isn't it?
If the math rigorously demands that the system must govern itself instantly to avoid the CIT collapse, are humans simply the biological scaffolding? Are we just slowly, deliberately building our own obsolescence into the multiplanetary substrate because the math gives us no other choice?
That is a lingering thought for you to mull over as you look at the devices surrounding you right now.
And speaking of big engineering visions, we have been looking at a bunch of other white papers and topics lately, and there is one coming up soon on semiconductor scaling, photonics, and the real limits of Moore's law.
Moore's law hitting the wall, come to think of it, that is going to be massive.
Exactly. We are going to dive deep into that one very soon, so stay tuned.
Whoa.
That was a lot. The mathematical limits of coordination are wild.
They really are.
We highly encourage you to seek out Martin B. Joseph's white paper. There's a profound, raw humanity in seeing these massive global shifts literally scratched out and wrestled with on a handwritten page. We invite your comments, pushback, and thoughts on the Convergence Lattice. We will see you in the next deep dives. Until then, stay curious and take care.